In this video, we're going to do an example of calculating the surface area of part of a surface using the formula for the surface area. The question says, find the surface area of the part of the paraboloid z equals negative x squared minus y squared that lies above the plane z equals negative 20. So first, we should get an idea of what the surface that we're finding the area of looks like. So what's going on is here's the positive x-axis, the positive y-axis, and the positive z-axis. And just going to do a dotted line for negative values. And what's going on is you have this paraboloid z equals negative x squared minus y squared. Well, hopefully you know what that looks like. This is negative parentheses x squared plus y squared. And hopefully you know that z equals x squared plus y squared is this paraboloid, is this bowl that kind of goes up. And then when you multiply by negative 1, the z values get multiplied by negative 1. And so you end up getting this shape, which is like this. Like that. And you want the part that lies above the plane z equals negative 20. So let's say z equals negative 20 is here. So you have this plane. And so you want the surface area of this part of the paraboloid. This part just keeps going on forever, right? This part of the paraboloid. Oops. So this. And let's call that surface S. So remember, the surface area of S, we need the formula for this. What you have to do is you have to start with the parameterization R of UV, a parameterization from a region in R2. Okay. And once you have that, the surface area is, surface area is the integral over that region R of R sub u cross R sub v, the magnitude of this with respect to volume, with respect to area, I mean. Okay. That's the formula. So what we need to do is we need to find the R of UV and the capital R region. And when you have something which is the graph of a function, see, in this example I have the graph of a function z equals f of x, right? My f of x, y is negative x squared plus y squared. This is my f of x, y. And so what I can do is I can use the parameterization R of UV equals u comma v comma f of uv whenever I have the graph of a function. And what's my region R? My region R is what I get when I project this surface down to the xy plane. Or well, in this case, I guess you project up to the xy plane. And when you take this surface and project it to the xy plane, what you're going to get is you're going to get the circular region. You're going to get this. And this is a disk, and we need to know what the radius of this disk is. So R is going to be this circular part in R2. And what you're doing to get this outside part of R is that's going to correspond to this circle, this outside circle, which is when z is negative 20. So to figure out what the radius is, well, this is the intersection of the plane z equals negative 20 with this paraboloid. So that's when negative x squared plus y squared is equal to negative 20. That's the same as x squared plus y squared equals 20. So what's the radius of this circle? It's the square root of 20, right? Because this circle centered at the origin is x squared plus y squared equals r squared. So r squared is 20, so r is positive, r is the square root of 20. So you have this region where the radius is the square root of 20. Okay, that's what r is. Okay, so now let's calculate the thing that we're integrating, this. So r sub u is going to be 1, 0, f sub u. R sub v is 0, 1, f sub v, right? We're just taking the partial derivatives of each of them with respect to r and with respect to u and v. Now we take the cross product. By the way, there's actually a simple formula for this, but it takes some time to remember. So if you take the cross product, ru cross rv, you're going to get, let's see, negative f sub u, negative f sub v, and then 1, right? So then the magnitude of ru cross rv is the square root of f sub u squared plus s sub v squared plus 1. This is a useful formula to remember. If you have the graph of a function z equals f of xy, and you want to find the surface area of a piece of it, you project onto the xy plane, and then you can also just use, once you project onto the xy plane, you can use this formula. Oops. Okay. So what does that look like? In this case, my f of uv is my z, right? So I have f of uv equals this is a function, it's negative u squared minus v squared. Right, that's if I take my u comma v in R and then plug that in, I'm going to get a point on my surface. Okay, so what's f sub u? That's negative 2u. F sub v is negative 2v. So then my r sub u cross r sub v magnitude is the square root of negative 2u in parentheses squared. That's 4u squared, and then negative 2v in parentheses squared is 4v squared. And then plus 1. So what I need to do is I need to calculate, so the surface area is the double integral over r of the square root of 4u squared plus 4v squared plus 1, okay, dA. Now to do that, I need to use, I'm integrating over a circular region centered at the origin. I need to switch the polar coordinates. So I need to use u equals r cosine theta, v equals r sine theta. And so now I'm going to replace my dA with r dr d theta, right? And then I have the square root of, so what am I going to get? Notice that this part is just going to be 4 times parentheses u squared plus v squared. So u squared plus v squared is r squared, right? And so I'm going to get the integral of 4r squared plus 1 inside the square root. And then times r dr d theta, and r is going from 0 to the square root of 20, and theta goes from 0 to 2 pi. Now we just need to do this integral. So let's do the inner integral. That's the integral from 0 to root 20 of square root of 4r squared plus 1 times r dr. Now what am I going to do this integral? I'm going to do a substitution, right? I'm going to use u equals 4r squared plus 1. And then I'm going to get du is 8r dr. And now I have an rdr. And so what am I going to do now? Divide both sides by 8. So I get 1/8 du is rdr. And I have to change the bounds of integration. So when I plug in my bounds, when I plug in 0 for r, what do I get for u? I get 1. What happens when I plug in the square root of 20? I get 81. So I have the integral from 1 to 81 of the square root of u times 1/8 du. And how do we do this? How do we integrate the square root of u with respect to u? We convert this to exponents, right? This is u to the 1/2 power. And then what do? We add 1 to 1/2, so we get 3/2, and then we divide by 3/2. That's the same as multiplying by 2/3. So I get 1/8 times 2/3 here. Integral from 1 to 81. From 1 to 81. Now I can simplify this fraction. 1/8 times 2/3 is 1/12, right? I can divide both sides by 2, and I get 1/12. And then I multiply that by 81 to the 3/2 power minus 1 to the 3/2 power. How do I do 81 to the 3/2 power? You want to take the root first and then the power. So 81, the square root of that is 9, and I have 9 cubed. Okay, 9 cubed turns out to be 81 times 9 is 729. So 729 minus 1. So I get 728/12. Not sure if that simplifies. Okay, the top and bottom are divisible by 4. So I guess I can divide both sides by 4. And then I get 182. Right? So that's my inner integral. And now we did the inner integral. We did this inside integral. And now we have to do the outside integral. So we have to integrate the inside from 0 to 2 pi. Well, that's easy. Because when you integrate a constant, you just multiply that constant by the length of the interval, right? Because when you integrate a constant, you get the constant times x, and then when you evaluate at the bounds, you just plug in the endpoints. So you get 182/3 times 2 pi, and that's going to be 364 pi/3. And that's the answer. So let's just review how we did this. We wanted to find the surface area of part of this graph. It's the graph of a function z equals f of xy. And when you do that, you can parameterize the surface. You have to parameterize the surface, and you do that by projecting the surface down to the xy plane. So you look at the xy plane, the points in the xy plane that are, well, in this case, above the graph, and you get this disk of radius, the square root of 20. And then to find the surface area, you use the formula. When your parameterization is r of uv equals uv f of uv, the formula simplifies, it becomes the integral, it becomes this. This is the thing that you're integrating. And then we calculated what that is. It was the square root of 4u squared plus 4v squared plus 1. So we needed to integrate that function over r. And we, in this case, since r was a circular region, we had to use polar coordinates. And once you use polar coordinates, okay, we had to do a substitution. And we ended up getting this as the answer. So I hope this gives you a better idea of how to apply the formula for the surface area. Thanks.